It's actually rolling. Any questions from you? I'm pointing at you, you 8. No questions?
Oh, I do have just one question.
Oh, Ross has got a question.
Oh, I'm not sick. So on problem 2, when it says to use any of the earlier results, does that mean we prove the general result that a scalar multiple of a row or column may be added to another column, or should we prove the specific? Because obviously we can. I guess I'm asking on the homework quiz. Are you going to want us to prove the general result or just the specific?
Sorry, you're asking about the current homework assignment?
Well, the homework quiz, because obviously it's easy to prove the general result on the homework assignment, but on the homework quiz we're going to be a bit more in a time crunch.
Are you talking about the homework quiz for this Thursday?
Yeah.
Oh, I haven't written that yet. I don't even know what I'm going to ask on it, so I have no idea.
Okay.
Yeah. So don't. I can't even answer that question at this point. But I'll take it into consideration when I'm writing the quiz. Okay. Any other questions? Fred, do you have any questions? No. Oh, that's good to hear. Good to hear. Okay. So I'm going to ask some intense questions of the question deck, starting with this one. Yes, Sophia, you got it. You're on there. I got a question for you, Sophia. Can I see your face? Okay, maybe I can't see your face. Are you there, Sophia? Oh, man, I don't think she's on there. She signed. Oh, man, Sophia. This is not going to go well for you. Okay. All right, that's fine. I got another card. And it's one of you, Sam Riddle. Sam, are you there, Sam? Oh, God, Sam's there. Thank God. Sam, hi. Hi. What was the final lesson we learned in the last lecture that connected the relevance of the determinant of a matrix to the existence of its inverse?
So the last thing that we learned was a matrix will only have an inverse if the determinant is not equal to 0.
Yes, exactly. And that is born from this expression that we actually derived, which said that the identity of a matrix is equal, or sorry, the inverse of a matrix A is equal to the classical adjoint of the matrix divided by the determinant of the matrix A. And of course, a matrix and its inverse automatically commute. Okay, and we went through the construction of the classical adjoint. I'll show an example of it today, but you should have done one in your homework if you're caught up on your homework. But at any rate, in order for this to be existent, det A has to be non-zero because it's sitting in the denominator. Okay, so good job, Ross, or good job, Sam. Sam, sorry, you're not Ross. You're Sam. I heard from Ross. Sophia, you still haven't shown up. Damn it. Okay, so so what we have just said, this is a condition for a matrix to have an inverse. Wow, there's even more of you on there. Wow. 8 people on Zoom. Wow, this is kind of interesting. Like, I don't, or they win? No, they're not winning. You're winning. Live always wins. This is a condition for a matrix to have an inverse, okay? But remember, we're studying linear transformations and operators. And we talked about the conditions that have to be met for linear transformations to have inverses. Here's a condition for matrices to have inverses. Is there a connection between linear transformations and matrices?
Yeah.
What kind of connection?
You can represent a linear transformation as a matrix.
Yeah, it's an isomorphism. It's a U are U kind of transformation. It's a U are U kind of identification. Okay. So this is just a matrix reflection of some of the arguments that we put forth in order to argue when and how does a linear transformation have an inverse. So just to show you how this pans out, I'm going to do a really simple example. Consider a rotation in R2. And we know what the matrix looks like. We'll just do cosine theta. And I just want to show you this example. It's really rapid, but I want to show you for one tricky insight. And because you might be using something akin to this on your homework. So det r theta, cosine squared theta plus sine squared theta, which equals 1, which does not equal 0. So clearly this has an inverse, and we can build that inverse using this formula, okay? So the formula says we want to take the classical adjoint of r theta divided by det theta. Det theta is, of course, 1. So this is 1 over 1 times the adjoint. And remember the adjoint, you take the row and column position. So this is the 1, 1 position. And you first of all raise minus 1 to the sum of those two labels. And then you do it over here, minus 1, 1 plus 2, minus 1, 2 plus 1, and minus 1, sorry, it's minus 1, 2 plus 2. And then you multiply it in forming this adjoint. You multiply each of these terms by what you get when you eliminate the row and the column associated with that element, and then take the determinant of the rest. So if I eliminate the cosine row and the cosine column, and I take the determinant of cosine theta, what do I get? Yeah, it's that simple. I told you this one would be easy. If I eliminate sine minus sine theta, what am I left with? Sine theta. And if I eliminate sine theta, and if I eliminate cosine theta. Okay, that's awesome. If we just multiply this bad boy out, I'll do 1 over 1. Bam, done. What about minus 1 to the 1 plus 1? Did you say negative 1?
That was me.
Yes, Joel.
When you do the adjoint, doesn't it flip the cofactor?
How? Doesn't it do what?
Flip the cofactor, the rows and columns.
What? Hold on. There's a reason for all my anxiety. Because you just pointed out exactly what I was trying to get to. Minus 1 to the cube.
Professor?
Yes.
None of us in the chat can see the board.
You can't see the board?
Not very well at all. It's super blurry. I can't make anything out. I don't think it's just me.
It's not.
Oh boy. Okay, hold on.
I'm so sorry. I had to take my dog out. He loves the snow, and it started snowing really hard.
Yeah, Sophia. Here you are. Is this any better?
A little bit, yes. A little bit, yeah. Can almost read it now.
Okay.
Actually, yeah, that's just good enough.
Okay, well, I don't know how much of the board you'll be able to read, because I'm going to write all the way over to here. Oh, man. I'm so glad so many of you are Zeusking it today, because that is really going to... Oh, hey, people. Go onto the course website and download the lecture notes, which are already there. And you should be able to follow everything I'm writing on the board by looking at what's in the lecture notes, okay?
That's a good idea.
And I'm going to pop this back up there so you can see the whole board, because this is I'm going to have to move you back and forth and able to see, in order for you to be able to see everything. And hopefully next time you come here live. So yeah, go download the notes from the website. I'm sorry, everybody. And we'll go from there. What was I doing? Oh, yeah. So minus, this becomes plus, and then becomes plus. And so there you go. R inverse is equal to itself, right? No, because Joel Bean was trying to sneak in this bit of information. When you do this, when you construct this thing, you also have to transpose it. And this is in the notes from last time. I'm not going to re-dig into the index notation. But you have to transpose this thing. And when you transpose it, you get exactly what you would have expected. This is the inverse of this. Okay, if you're not familiar with rotation inverses, you just swap where the negative is on the sign. Okay? Now, So here is a demonstration of how this expression can be used to form a matrix inverse. What I would like to do now is apply it to a more abstract example. And it's the example with which you're hopefully getting more and more familiar. And we're going to beat on it rather frequently until we're all there. So consider the derivative operator acting on Pn. And we'll just use P1 for simplicity. So remember, the derivative operator had no inverse. Okay? And also recall, and these will be useful later on, so I'll write them up here, the actual expressions for D. So we have that D takes the value 0, 1, 0, 0 in the basis 1t. Okay, so that's if you're writing your polynomials based on a constant plus a linear function in t. And if you take d in the basis 1 plus t, 1 minus t, then d takes a different form, which I expressed to you at some point in the past, and we'll bring this up again later, of 1 half, 1 half, or 1 half minus 1 half, 1 half minus 1 half. And okay, so first and foremost, what's the easiest way to realize that there's no inverse to D? Yeah, the determinant of these is 0, and those are quick determinants you can do, okay? But what I would like to do, instead of focusing on this matrix language, I would like to go visit back to some of the properties of matrices that we had explored. And I'm going to label these by their number, so it's in that list that we had last time. But from property 2, oh shoot, I don't remember what property 2 was. Property 2 is if all of the, yeah, if any, yeah, right. If any row or column equals 0, then that A equals 0. Okay? Well, here you go. In this basis, clearly you have a row or a column that's 0. In this basis, it's not so obvious. Okay? Remember, these represent the same operator, so if one of them doesn't have an inverse, the other one definitely doesn't have an inverse. But that just means this will allow us to select out determinant 0 operators in certain bases, but you can go to another basis where it's not as obvious. Okay? However, from property 5, if 2 rows or columns, goodness, are the same, then det A equals 0. And of course, in this case, it's clearly obvious that the 2 columns have the same values. Okay? From property 8, if 2 rows, columns are linearly dependent, then the determinant of A equals 0. Okay? Clearly, either the 2 rows or the 2 columns, either one, are linearly dependent on each other. Okay? Of course, you could just take the determinant. All right? So in this case, it's obviously simplest and most straightforward just to take the determinant. But if it gave you a 100 by 100 matrix, you might not have the time or energy to take the determinant, but if you saw that all of one row was zeros, or that 2 rows were the same, or that one row was a linear combination of another row, you could automatically conclude that the determinant is 0. Therefore, the inverse does not exist. Okay. So, yeah, so I'm going to go from there. Oh, no. thing, this over. Okay, here we go. Any questions before I move on? Good, excellent. All right, so now we're going to dive down into index land a bit, and it's going to hurt a little bit, but you know, it's okay. In the end, I will just summarize what we're doing, but you know, just bear with me as we wade through the index land. Okay, so now what we've been doing is we've been focusing on linear transformations. And linear transformations, A, have this property that if I hit an AX with the linear transformation, then it maps the vector x to a vector y, where both of the vectors x and y sit on the vector space V. Okay? Now its action can be expressed in terms of the components of a vector or the transformation of the basis of a vector, because these are linear transformations of vectors. And remember, a vector is a sum over the components alpha mated with the basis vectors xi. And so you can imagine A operating either on alpha I or on xi. And usually the way that we talk about this is we actually use the action of the linear transformation on the components because we want to leave the basis fixed. So what I have in mind is if I had some coordinatized space and then I have a vector V, or no, I'll call it X. And we're going to break it down into its components along a basis x1 and a basis x2. Then what we might be interested in doing is a linear transformation with a fixed basis. Where maybe our linear transformation is going to take that vector and it's going to rotate it into that vector. Okay? So this is good that we're allowing A to act on the coefficients or the components or the coordinates, or different names for this thing, and we're going to leave the basis untouched. You can alternatively rotate the basis and leave this untouched, okay? But there is a different thing that we can do, which we're going to discuss. And that is, we can actually skip thinking about a linear transformation for a moment and think about, let's just change the basis. Now here I'm talking about you can change the basis and you can affect this transformation, but I actually don't want to change the vector, I just want to change the basis. So what I have in mind is a situation here where I have the same vector, x. So notice it's the same vector. However, we're going to be utilizing a different basis to describe it. Okay? So I want you to understand this map before I beat it out in detail, okay? This is what some might call an active transformation versus a passive transformation. Because at the end of the day, this has y aligned with the v-axis, and this has, well, x. Huh. No, that's supposed to be y, because this is a transformation of x. This is just x. I'm not doing a linear transformation in here. I'm changing the basis. Okay? But nonetheless, the vector is now aligned with the coordinate axis. Okay? So you've probably heard of this in the context of rotations, right? You know, you can either think of rotating the vector or rotating the coordinate system. they're equally interchangeable. Okay? Well, it turns out that for rotations that's true, but you can't do that for an arbitrary linear transformation. What I mean is you can't take an arbitrary linear transformation and cast it only in terms of a basis change. For example, you know, here's a linear operator. Can you take all the vectors in the space and do a basis change and get that for all the vectors in the space? No, but that's what A is going to do to all the vectors in the space. It's going to turn them into 0. It turns out that rotations are a very special subset of linear transformations that can be reflected in a coordinate basis change, but most generally linear transformations can't. Okay? Do we follow? So we want to meticulously follow through, okay, how do we take linear transformations and their actions on vectors and do a basis change on them? Because notice here, we haven't changed the vector at all. The vector's the same, we're just changing the basis. So what we want to do is we want to roll into the story what happens to a transform vector. Okay, so I got some good stuff in here.
Quick question.
Yeah.
Am I interpreting what you said correctly by thinking we can't always do a passive rotation?
Right. Oh, no, you can always do a passive rotation.
Okay.
But not a passive linear transformation.
Oh.
Yeah, so rotations are a special set because rotations are intrinsically linked to your coordinate basis.
Oh, okay.
However, there are linear transformations which cannot be mimicked by just changing the basis. One example is A equals 0 because it takes every vector in the space and collapses it to the 0 vector. Now tell me, how can you have a space where every vector in that space becomes 0 because of your change in coordinates? Right. And there are other linear transformations that won't work as well. Okay, so I'm just pointing out rotations are a special set of linear transformations which happen to also correspond to basis changes, but that's a very special set. Generally, linear transformations are not that special. Okay? All right.
So as we go forward, are we excluding some linear transformations?
No, we want to have a discussion that involves all linear transformations. That's what we're about to do.
Gotcha.
Okay? Okay, so yeah, so doobie-doobie-doo. Okay, so for an arbitrary linear transformation A, y equals ax generally does not equal x. That is, most linear transformations take vectors and exchange them with other vectors, or replace them with other vectors. The identity is obviously boring. Okay, the identity takes every vector and gives you back the same vector. And there is another special kind of vector which, if you act on it with a linear transformation, gives you back the vector. We'll talk about that in a minute, eigenvectors. But we're not going to talk about it yet. But generally speaking, a transformation A takes one vector and turns it into another vector. These two vectors do live on the same vector space. But a basis / coordinate redefinition does not. So what I mean is, if I'm in a totally prime system and I just want to be really determined and call this prime, then I can write x prime as some linear transformation B, and I'm going to tell you exactly what that B looks like in a minute, so that's why it's in parentheses, or it's in quotation marks. But if I take the x here, and I do the coordinate transformation on x, then I get x prime, but this has got to be the same as x. Because we're not actually changing the vectors themselves, we're just changing the basis. Now if you look at this, you might say to yourself, well, this is pretty simple, that's I. Go ahead, say it, somebody.
be simple. It's got to be I.
Thank you very much. I really do appreciate your camaraderie. Yeah, so this is roughly I, right? Well, that's because you're thinking of this as a linear transformation, as an active transformation. It's passive. So it's not quite I, but let me go into detail, okay? And we'll explore what this is. So here we go. I'm going to make some room. All right. So we have x. Yeah, I'll do it here. Okay. So we have x is the sum over I of the components of the vector x times the basis x. And we want this to be the same as we would get if we did a basis change. That's this kind of transformation, not this. If we did a basis change and got a new set of components, which, look at it, this is going to have different components than this did. So you expect the alpha i's to change. And you have different vectors, basis vectors. These basis vectors are not the same as these. So each of these will change, but the combination, which is the actual vector, should be the same. We following? Good. That's awesome. Okay, so the way that this is going to work, pretty much, and I'll go into more detail, is that the components are going to change with a factor of b inverse, and the basis vectors are going to transform with a factor of b, and I still haven't told you what b is, where these two things, so this is your alpha I prime, this is your xi prime, but clearly b times b inverse is 1, so this is really just alpha I times x. Okay?
Don't we have to sort of assume that all of those things commute to be able to say, like, plugging in the b inverse and b where you did works out?
Yeah, I'm going to be more careful in a minute. So yeah, I appreciate the question of, like, can you commute this past this to actually hit that b in with it? And I'll get through it in the subscript notation in just a minute. But this is the rough idea, because now I have a question. And Lucas, are you here or are you there? No, you're on there. Lucas.
Yes.
Lucas. Okay, here you go. Are you ready? This is a big one. In order for the transformation B to take me from one coordinate system to another coordinate system, what about B must exist?
It has to have an inverse?
Yes! That's awesome. Sweet. Awesome. That's perfect. Yeah, so you'll notice a lot of linear transformations don't have inverses. A equals 0 does not have a linear inverse, or it doesn't have an inverse. But these clearly do. I mean, if you're going to change coordinates, you can always go back to where you started from. Okay? So this B inverse is going to play a role in the transformation. Okay, we'll get through the details now. Okay, so if B equals B11, B12, B21, dot, 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 dot. So these are the elements when I write little b, 1, 2, 1, 1, 2, 1. These are the elements of the transformation B. Then we have xi prime, that's this guy, is equal to the sum over j of bji xi. So this is the rule for the linear transformation of a basis vector that I gave you some time ago. And you'll notice, for those of you who remember this, you're summing, no, that's the xj. I can't remember where on my page I am. Yeah, sorry, this is xj. Okay? You're summing over the first index of the tensor, or sorry, of the matrix, not the tensor, of the matrix, and then the index on the vector. This is not matrix multiplication. Okay? In fact, if you wanted to kind of view this as matrix multiplication, you would reverse the order of these. Okay? And alpha I primed is equal to the sum over k of B inverse ik alpha k. Okay? Scott.
Yeah.
Oh yeah, you're here, sorry. I can't recognize you with that mustache. Do you have that mustache?
No.
Okay, that's what I thought.
Not right now.
Okay, yeah, that's totally confusing to me. I have a question for you. Here I put little b,
Okay.
and here I put big B. Could I not just put like B, J, K inverse? Or sorry, I.
I want to say no because you didn't. But
Well, it could have been like literally, I could have just, oh shoot, man, I always capitalize stuff and I shouldn't have capitalized it, but it did. No, you got to capitalize it. Can you imagine why I have to have capital B there? You got to phone a friend.
Sure.
Go for it.
If you have the lowercase that you're referring, you just put 1 over a scalar instead of actually using the inverse.
Exactly, exactly. You got to be really careful. Okay? Because this is just taking an element of the matrix B and doing 1 over that. That is not how you build an inverse matrix.
yeah.
Okay, so this is saying take the matrix inverse and then take the ikth element of it.
Okay.
Okay, so that's why that capital B appears there, and I'm actually going to write it again so it actually looks like a damn capital B. Okay, sorry. All right. Yeah, okay, so ik, alpha k, pi, boom, there we go. All right, so now, are we ready? Because now it's going to get index gymnastics heavy. Now what we want to do is we want to consider, are you ready, y, which has its own set of components. We'll call them bi. And of course, y, which is the result of the active transformation, y can be expressed in terms of the original basis xi. Okay, but now what I want to do is I want to take this and I want to map it to a transformed version of the coordinates. So I don't actually have that picture up here and I'm not going to draw it. But the y vector that you get after you do the coordinate transformation should be the same as the one you started with. Okay? So what we should have is that y equals this, but y also equals the transformed beta and the transformed xi. Okay? These should be the same.
Wait, you said the transformed xi, but you did not prime that?
Oh, sorry, yeah, I should prime it. Sorry. Okay? Yeah.
Xi prime sort of looks like it would just be you transpose B and then do matrix multiplication. Is that right? The BJI xj.
We'll get to it in a minute. It's going to be even more precise than what you see here in just a minute. Because, I mean, this is still evading the full index land because you don't have the indices in the B, so you can't really figure it out, but we're going to get through that in just a second. Okay? Well, no, actually,
I'm just looking at the xi prime equals the sum.
yeah. So hold on. Let me think for a second. So, okay, so what you want to argue, and this is fine, is that sum over I alpha I xi is equal to sum over I alpha I prime xi prime, using these two expressions, right? Okay, so first of all, I can reorder these, because this is just a scalar times a thing. So we can alternatively write xi alpha I is xi prime alpha I prime. And then if I substitute in for the transformed version of xi prime, this guy, then I have sum over I, sum over j, b, j, I, x, j. And then if I substitute in for alpha I prime this version, okay? Now, this, if you want to understand it as matrix multiplication, you would reverse the order of these two things. Okay? So if I reverse the order of those two things, okay? What is this?
That is the identity.
It's delta j k, which says that these have to be the same, which says that these have to be the same. And you get back that. Okay? Does that make sense?
Yeah.
Okay. Because it's going to get even uglier than this. All right, so, all right. Ugh. Okay, so, now, we have to remember how exactly we get y from x, because this is our starting point, and we want to map the active transformation followed by the passive transformation. So remember that if we're going to do an active transformation, we can imagine that A is only acting on the coefficients or the components or the coordinates or whatever. So the BI's are coming from A acting on the alpha i's. Similarly here, we have the coordinate rotated version of A times the sum over the components of the vectors times the basis vectors in the rotated coordinate system. Okay? Here we go. Woohoo! So remember how the linear transformation A acts on the components. So we have sum, oh goodness, I, sum j, A, I, j, alpha j, x, I. Okay? Where the aij's are just the components of the matrix realization of this linear transformation. And when you're transforming the components of when you're transforming the components of a vector, then you're actually just doing matrix multiplication. Okay? Similarly here, we have an expression of the following form, and I'm going to write this a little bit differently. I'm going to write sum over I, alpha I prime, sum over j, A, j I primed, xj primed. Okay, I mean, I'm collecting the alphas out front, and I'm just combining these two, but you can reorder these things because you're using the summation convention, and the order of things doesn't matter when you're using the summation convention. Okay. You ready? You sure you're ready? Get ready. Here we go. Okay, we know how these change. We know how this changes. Let's put it in. So what we get is sum over I, sum over k, b inverse, I, k, alpha, k, sum over j. Remember when I told you this was going to be index gymnastics? That's what it feels like. Okay? Is that good to everybody?
Good is the strong word.
Good's a strong word. It is a pretty damn strong word.
I think I pulled a muscle.
Yeah, I think I pulled a muscle writing these notes. Okay, here we go. So this is sum over L, sum over... It's funny when my brain, like when it thinks about what it's writing and then it writes something, they just get mixed up and it's like, okay, anyway. And I will go back and I'll re-summarize this in a moment without all the indices. But I got to do it honestly. Just to show you that the crap works. Oops, alpha K XL. Whew. Okay. Now, what do I want this thing right here to be? Max. Are you there, Max?
Hey, yeah, sorry, can you repeat the question?
Max, what do I want the thing in parentheses right here to actually be? If this is equal to this, what should this thing right here equal?
Honestly, I'm not sure. It's a little hard to see the board for me. My internet's been pretty bad today.
It's hard for all of us to see. Yeah, I'm not quite sure what you're talking about.
Read the notes from class. It's in the notes.
I'm looking at them, but you lost me a second ago, and I can't really compare with where you are on the board to what the notes look like because I can't see the board.
I'm there.
I'm in the same boat.
I'm there, and I'm asking, what is this equal to? And that's the answer.
Third line from the bottom on the notes.
Yeah.
And
Oh.
so you're asking what the big thing in parentheses goes into?
No, what does this have to be equal to in order for this y to be equal to this y? I'll give you the expressions you should compare. Compare this expression with this expression.
I'm going to say ALK.
Yes, thank you. That's exactly right. Okay? So what we find, excellent work. ALK is equal to, oh my goodness, sum over I, sum over j, B inverse IK A J I prime B L J. Or you could take this and ask, what is A prime in terms of A? Okay? Because that's really what we were after. We were after what is the transform basis, what are the transform coefficients. We would like to know what are the transform components of A. So if you want to know A prime in terms of A, then that's just the sum over L, sum over K, B inverse JL ALK BKI. Okay? Now, Seth.
Yes.
What is the beautiful simplification here versus here?
Yeah, we have our notation is we can do matrix manipulation.
Exactly. Since now in this expression you have the repeated indices immediately adjacent, this just constitutes matrix multiplication. Okay? This is saying that A, when I do a basis transformation, that is realized by a matrix B, that it's just B inverse times A times B.
That was a complicated way to diagonalize that. Is it diagonal?
It's not, well, we're going to get to that a little later on. We're not diagonalizing it yet. But there is an interesting observation. If you have any matrix A that can be related to another matrix A prime through a transformation of this type, where you're acting with some linear transformation on the right and its inverse on the left, then A and A prime are similarity.
That doesn't seem like a whole sentence.
Well, it's a similarity transformation relating them, or they're similar. We'll just say similar.
I like that.
Okay.
I think that's correct.
I mean, I believe it in the house.
Okay, so let me yeah, I won't worry about that last line. I gotta get through some stuff. Okay, so now I wanna reiterate. You know, this is kind of it kind of seems like a melting pot of ideas, like linear transformations, There are two categories of linear transformations which I'm talking about. There are the active ones, and any linear transformation can be realized as an active linear transformation. And what I mean by active is you're going to keep the basis in the vector space the same, and then you're just going to have a map, which is going to grab every vector in that vector space and send it to another vector. It could be sending them all to 0. That's fine. 0 is an element of the vector space. Okay? There is a very special type of transformation which leaves every vector in place. It doesn't change any of the vectors, positions, sizes, anything, but rather it grabs the basis in the space and it rotates it, or it transforms the basis to a different basis. It's not necessarily rotations, it could be something more complicated. We'll see in a second. Okay? This is a linear transformation, but its action on things has to be a bit different. For example, if I do a linear rotation, if I do a rotation by pi, and then I want to, and this is going to act on a vector v and give me a vector v prime, and then I want to know how does this behave under a rotation by 3 pi over 2, all I do is I hit this with another rotation matrix. Because when you do this transformation, you get a vector back, and you can hit that with another linear transformation. Notice I'm not hitting this thing with the inverse of this on one side and this on the other. Because all I'm doing is I'm taking an active linear transformation, and then I'm doing a second active linear transformation. That is different than just trying to change the basis and leave all the vectors the same. There, we have a certain rule for changing bases, we have a certain rule for changing components, and we have a certain rule for how to change linear transformations which you have acting on that space. Okay, you on board? All right, good. Okay, so let me get rid of some of this, and we will move through another example, which is conveniently already partially done for us on the board. So we'll just remind ourselves of the results. Okay. So let me just say something very quickly, and that is, and these are very easy to prove. Based on this right here, you can prove the following two theorems. Det A, and by the way, this is an operational definition that they are similar. So the definition of similar is that you satisfy that the two matrices A prime and A are related by a transformation of this type. If they are similar, then det then det A equals det A prime. Can anybody prove that for me real quick?
Because the determinant of the product of matrices is the product of determinants. So you take determinant of this side, and then you group the B prime and B, it's det I, which is 1.
Exactly, okay. And then also we have that the trace of A equals the trace of A prime, which you can derive from similar considerations. Okay, so these are really pretty trivial to derive from this definition. Okay, so here we go. All right, let's go back to this example. So let's think about D, which is of course just d by dt on P1 with a function alpha 0 plus alpha 1t, which of course can also be written as 1/2 alpha 0 plus alpha 1, 1 plus t, plus 1/2 alpha 0 minus alpha 1, 1 minus t, depending on whether you want to work in the 1t basis or the 1 plus t, 1 minus t basis. Okay, so remember that in the 1t basis, we have if alpha is given by alpha 0, alpha 1, this is 1, this is t, then d alpha is given by alpha 1, 0. Or y, which equals d alpha, is given by alpha 1. Or sorry, y is dx, but I'll just write it like this. I'll say y is alpha 1. Okay? And in the 1 plus t, 1 minus t basis, we have that alpha primed is 1/2 alpha 0 plus alpha 1, 1/2 alpha 0 minus alpha 1. And then d primed alpha primed gives me 1/2 alpha 1, 1/2 alpha 1, which is y prime equals alpha 1. Okay?
What is y?
Y is what you get when you're acting on dx, where x is the sum of alpha and xi. But we're just having the linear transformation act on the coefficients. We're not writing this out in terms of the transformation of the coefficients and the basis vectors, because we're going to assume here right now the basis vectors are fixed, the basis vectors are fixed. So if I'm going to do the linear transformation, the only thing that's going to transform are the components, not the basis vectors. Don't worry, going from here to here is a change of basis vectors, and that's what we're about to explore. But once you fix the basis set, okay, once you say we're going to work in this goddamn set of basis vectors, nothing else ever again, then you don't need to carry them around throughout your calculations. You can just work with the components of things, which is what you're used to, okay? So you can talk about the linear operation on the components, okay? But at the end of the day, what you're really describing are vectors. The vector here is the same as the vector here. I mean, because this is all done in the transformed coordinate basis from this. Okay? So I'm just going to show you that all of this results from what we just talked about. Okay, so very quickly, oops. Warn you guys, don't ever get old, it really sucks. Okay, so here we go. The B inverse that we need in order to make this work is 1/2, 1/2, 1/2, minus 1/2. Because if I take B inverse and I hit alpha with it, I get alpha primed with it. hit this with this, you get this. Everybody see that? And remember, this is how the coefficients change. They change with a factor of the matrix inverse. It was written before with all the subscript poison, but I'm trying to leave that out because we got matrices to work with. Okay? So now we have B inverse on the derivative operator B times B. This is D prime. Okay? Well, you can do this. You can take you can take this. You can hit D with it. D is up there. And then you can multiply by the inverse of this. The inverse of this is this. The inverse of that happens to be 1, 1, 1, minus 1. And you get 1 half, 1 half, 1 half, minus 1 half.
Shouldn't there be another minus?
Sorry.
Yeah, we need a minus.
And the top right?
Yeah.
So, oh, yeah, you're right. You're right. Sorry. Bam. Okay. So so look, when I derived this in a previous class, I didn't do this transformation. I didn't have this transformation in hand. I simply took this polynomial and wrote it like this and said, okay, what's the matrix version of the derivative acting on this? And we got this. And then I said, okay, what's the matrix version of the derivative acting on this? And we got this. Okay, so we were just comparing two different bases. Now we're transforming between two bases, which of course has to give us the same results. Everybody on board? Yeah, go ahead.
So with D prime, we're working in the 1 plus D 1 minus D cases.
Yes. With D prime?
Yeah.
Yeah, good, good.
Where would that be reflected in the operation to actually go from D to D prime? Like, could you construct B from the basis vectors that you want?
Yeah, that's how I constructed the B. So I constructed B inverse so that this was true. Make sense? I mean, I just looked at alpha primed and alpha and said, what does B inverse need to be? And that's what it needs to be. So yeah, the B's are intimately related to where you're starting and where you're ending up after the transformation. Okay, other questions? Good. Okay, oh yeah.
Are we gonna revisit this when we get to infinite
Yes.
dimensions?
Yes.
Okay, cool.
Yeah. So we're going to go infinity and beyond a little bit later. Okay, so we're going to now start with, remember, this topic actually started a couple of days ago when I said we've got all these matrices, how can we get scalars from matrices? And it turns out there's another way to get a scalar from a matrix, and I can't remember, was it you? I think it was you that suggested. Yeah. Getting scalars from matrices. What do you recommend?
Determinant.
No, maybe it was you.
What?
Who said eigenvalues?
Josh, he's
Sean said eigenvalues.
Well, maybe one of you said eigenvalues. Too bad you're not here. We'd give you credit. Okay, so eigenvalues are yet another scalar that emerges from doing manipulating linear transformations. Okay, so I think I'm gonna, you all should know about eigenvalues. So I think I'm going to rather quickly.
How is it that you're this caffeinated, but you're still behind on your lecture notes?
I know. Well, it's funny because.
You've been talking so fast.
I know, it's kind of crazy how far behind I am on my lecture notes. Okay, so you guys, you might or might not be completely comfortable with eigenvalues and eigenvectors and so forth. How many of you are completely and totally 100% comfortable with the notion of eigenvectors and eigenvalues? All the hands on the screen went up, none of the screen hands in the room. No, I'm just kidding. I can't see any of you. Oh, no, I see one person. Boom. And you started to raise your hand and you put it down. Okay, it's fine. So I will be very cursory with my eigenvalue, eigenvector story until we hit the hard stuff. So, okay. So first of all, let's cast this in the language of what we've been doing. So normally, ax equals y, where y does not equal x. That's the action of a typical linear transformation. Okay? But obviously, we can have ax equals lambda x, where we'll go ahead and index all these by I, because there could be I of them. This is a special linear transformation and a vector which is related to it, because you get back the same vector at best scaled by some scalar coefficient. Okay? This is, of course, the eigenvector of the transformation A. This is the eigenvalue of the transformation. Okay? And of course, what we're left to want to find are the eigenvectors and the eigenvalues and the eigenvectors associated with a transformation A. So given A, can we find the lambda i's and the xi's? That's rather different than what you tend to encounter in problems like this, because in problems like this, you're usually given A and given Y, and then you're asked what are the x's. Okay? And there, if you can just find an inverse of A, then you've solved it. Because you just apply A inverse to each side, and you've got your x's. Here, though, A is all you know, and you want to figure out the rest of this information. Okay? But you're aware there's some work you can do that's not that difficult. So consider, and a lot of this will be review. Okay? Can M inverse exist if xi exists? Yes or no? Jacob? No, why?
Yeah, I guess obviously it has to do with subtracting out the eigenvalues from the diagonal.
Well, if M inverse exists, can I apply it to both sides of this and get that? Which is not a very interesting solution. So we don't want M inverse to exist where this is M, okay? Wait, is that M?
It's like I lambda.
Thank you, yeah, because lambdas are scalars. This is represented by a matrix, this is represented by a matrix. This has to be a matrix, so you just multiply the scalars times I. But nonetheless, you want the inverse of that not to exist. What feature guarantees us that the inverse won't exist?
The determinant is 0.
Thank you. So, we know that we're running into an eigenvector, eigenvalue situation dealing with those things if we demand that. Okay? How many solutions to this are there? Well, first of all, how many unknowns are in here? Well, there's the lambda i's. Those are the only, this is the identity, that's well known. This is the matrix you're starting with. So how many lambda i's can you possibly have? The dimension of A, which we would say A is n by n. So how many i's? N. That's the number of i's? to that in a minute. We'll come to that in a minute. Okay, so now here's an interesting observation. And this is where sometimes you just can't escape imaginary land. Okay? I could have a real, a matrix representation of the linear transformation, and it could have all real elements. But it might be the case that the eigenvalues and the eigenvectors are imaginary, or complex at least. Okay? And of course you know this because you can write down a real polynomial expression. All the coefficients in this are real. X is an unknown, but what is X? Plus or minus I. Okay? So this is going to be a situation where imaginary or complex is going to force its way into what seems like an otherwise real story. Okay, so we have this condition, we write down the polynomial expression that results from it, we solve it, we get the lambda i's, then we go back and we revisit this condition and we insert a lambda I, and then we find the corresponding eigenvector xi, okay? So let me very quickly run through an example that shows you this, where there's obvious answers and there's not so obvious answers. So consider in the vector space R3, the rotation matrix around the xy axis. Okay? Can anybody give me an eigenvector and its eigenvalue? Huh?
1 is an eigenvalue.
For what eigenvector?
0, 0, 1.
Yeah, folks, I mean, you're rotating in the xy plane. So what do you not change when you're rotating around xy? Z. So if I write down Rxy 0, 0, A, it doesn't have to be 1, but I could make it 1. Then this is going to give me plus 1 times 0, 0, A. We on board? I did not solve the determinant of A minus lambda I. I didn't solve that to get this. I just used inspection. Because this is a transformation, and I can ask myself, is there any vector which remains pointing in the same direction after I do this transformation? And it can be rescaled by a coefficient. Sometimes that coefficient is just 1, okay, which in this case it is. So you have intuition for eigenvectors, hopefully, but there can be eigenvectors and their eigenvalues which are not so damned intuitive. And for those, you have to go through the systematic procedure. So let's go through that. So we want to do det R minus lambda I times I. And I'll just do this very quickly. This is going to be cosine of theta minus lambda I, cosine of theta minus lambda I times 1 minus lambda I, plus sine of theta times 1 minus lambda I. Yes. And I want that to be 0. Okay? So multiplying this out, lambda I cubed minus 2 cosine theta plus 1 lambda I squared plus 2 cosine theta plus 1 lambda I minus 1 equals 0. Okay? We've got a cubic in lambda I, so we expect 3 solutions. They could all be the same, but we expect 3 solutions. So what are they? Well, first of all, 1 is a solution, reflecting what we had from our intuition. Moreover, e to the plus or minus I theta solves this. which you can piece together in your head. All right? Each of these corresponds to an eigenvalue. So what we can do is take each of them, plug them back into this expression using our x. Using this. Oh, sorry. That's the particular one. Okay, so we can solve these for what the corresponding eigenvectors are for e to the I plus and minus I theta. And what you find, and I do this in the notes in detail, but I'll get you out of here on time, is that x1 is, of course, 0, 0 times a, or 0, 0, a, where a is along the z-axis. x2 is a minus ia 0, and x3 is minus ib b 0. Okay? Can you give me an intuitive description of this? Neither can I. But there you go. You have complex eigenvectors and their complex eigenvalues for this otherwise completely real operator. But there's no way to avert complexity sometimes. Okay, so we're going to stop there. And when we come back on Thursday, we'll talk about degeneracy of eigenvalues and eigenvectors and so forth and so on, but more later. All right, thanks you all. Are there any questions before you bug out? Any questions from you guys?
Not really with us.
Okay, all right.
Bye, Zoomies.
Bye, Zoomies. You were told bye from the audience.
Bye, Dr. Thorne.
Bye.